A silent rain of atomic bullets constantly strikes our planet. These are cosmic rays, subatomic particles hurled across the universe at nearly the speed of light. They are enigmatic because each one is a broken piece of a cosmic crime scene, a messenger from events so violent we can barely comprehend them. By the end of this journey, you will know the 25 greatest puzzles these particles present, from freakish lone projectiles with the punch of a baseball to patterns that hint at galaxies gone wild. What could possibly accelerate a single particle to such impossible energy? Why do some seem to come from the empty void of space itself? We are about to count down the most baffling cosmic ray mysteries ever recorded. What do you think is the universe's most powerful particle accelerator? That silent rain holds a single drop of pure terror. In October of 1991, a particle slammed into the atmosphere over Utah with a force that should not exist. Scientists running the Fly's Eye cosmic ray detector saw the data and could only whisper one phrase, the "oh my God" particle. Its energy was beyond comprehension. Imagine a single proton, a subatomic speck smaller than an atom, carrying the kinetic energy of a baseball hurled at 60 miles an hour. To achieve that, this lone particle had to be moving at 99.9999999999996% of the speed of light. It was moving so fast that, from its perspective, the entire width of our Milky Way galaxy would have been compressed to the length of a football field. This single event shattered every model we had. Nothing in our known universe, not the swirling disks of black holes, not the shockwaves of exploding stars, seemed powerful enough to give one tiny particle such a monumental kick. The debate ignited instantly and still burns. Did it come from some monstrous, hidden accelerator in our galactic backyard, a source so close and violent we have simply missed it? Or, more unsettlingly, does its existence point to a fundamental gap in our physics, a new law of nature that allows for accelerators we cannot yet dream of? The "oh my God" particle was a message from the cosmos, written in energy so extreme it simply said, "You do not understand how the universe works." The "oh my God" particle was not alone. Decades later, in May of 2021, a network of detectors spread across the Utah desert, known as the Telescope Array, recorded another impossible arrival. Scientists named it the Amaterasu particle after the Japanese goddess of the sun, a being who illuminates the world from the heavens. Its energy was staggering, a rival to that legendary 1991 event, carrying the punch of a professionally thrown fastball. But its origin story was, if anything, even more baffling. When researchers traced its path backward through the cosmos, it pointed not to a brilliant galaxy or a known cosmic beast, but into the local void. This is a vast, desolate region of space bordering our own galactic neighborhood. A place so empty it measures hundreds of millions of light years across with almost no galaxies to speak of. It is the universe's closest equivalent to absolute nothingness, so the question becomes paralyzing. What catastrophic event could possibly have occurred in that profound emptiness to forge and launch a particle of such godlike power? The discovery was the result of a monumental, decades-long international collaboration, a testament to human persistence in chasing these ghostly signals. Yet the answer it provided was simply a deeper, darker question. It suggests either our understanding of the void is completely wrong, and it seethes with invisible, violent activity, or that our models of how these particles travel through space are fundamentally flawed. The Amaterasu particle did not illuminate the cosmos for us. Instead, it cast a longer, more confusing shadow over the map of the known universe. These impossibly powerful individual particles present one kind of mystery, but what happens when you step back and look at the map of the entire sky? A deeper, more subtle pattern emerges, known as the anisotropy enigma. For the longest time, scientists assumed the very highest energy cosmic rays should arrive at Earth from all directions equally, a perfect uniform rain. The universe is vast and chaotic, so any sources powerful enough to create them should be scattered randomly across the cosmos. Yet when researchers painstakingly mapped millions of these ultra-high energy events, they found a faint but undeniable imbalance. The map was not smooth. It showed a dipole, meaning the rays come slightly more from one broad region of the sky and slightly less from the opposite direction. Imagine a gentle cosmic wind blowing these atomic bullets from a particular quarter of the heavens. One leading theory points to our own motion. Our entire Milky Way galaxy is sailing through space, and as it moves, it might be plowing through a relatively stationary sea of cosmic rays. This would create a kind of headlight effect, making it appear as if more particles are coming from the direction we're traveling toward, and fewer from behind us, much like a runner feels more raindrops on their face than on their back. Another compelling idea involves the invisible scaffolding of the universe itself, extragalactic magnetic fields. These faint, pervasive magnetic fields stretching between galaxies could be subtly bending the paths of these charged particles over millions of light years, gently focusing them from certain directions and deflecting them from others, creating those observed hot and cold spots on the sky map. This anisotropy is not a violent shout like the "oh my god" particle, but a persistent, whispering clue. It suggests that even the most powerful events in the universe are not truly random, that they are woven into a larger, ordered fabric we are only beginning to perceive. The pattern is a fingerprint, and we are still trying to understand the hand that made it. This subtle cosmic wind points to a larger structure, a hidden architecture in the rain itself. If we could plot every cosmic ray ever detected, from the faintest drizzle to the most violent thunderclap, on a single graph of energy versus abundance, we would see a shape that has haunted astrophysicists for generations. The line plummets steeply downward, telling a simple story: the higher a particle's energy, the rarer it is. But then, at a very specific point around 10 to the 15 electron volts, the line makes a sharp bend. This is the cosmic ray spectrum's knee. It is the first of two great bends in this cosmic curve, and it represents a fundamental shift in the story these particles are telling us. Below the knee, the particles are relatively plentiful and their origins are somewhat clearer. The leading suspects are the shockwaves from supernova remnants right here in our own Milky Way. Imagine the expanding shell of a star's violent death acting like a natural, galaxy-sized particle accelerator, sweeping up protons and electrons and hurling them outward for millions of years. This process seems perfectly capable of creating the vast sea of lower-energy cosmic rays that constantly bathe our planet, but the knee asks a critical question. Why does the supply of these galactic particles seem to drop off so abruptly at this specific energy? One compelling explanation is that this is the limit. The knee may mark the maximum punch our galaxy's accelerators can deliver. No supernova shockwave, no matter how powerful, can push a particle beyond this energy threshold. It is a speed limit stamped on the machinery of the Milky Way itself. Another theory suggests it is not about creation, but about escape. Particles below the knee might be trapped by the galaxy's tangled magnetic fields, bouncing around for eons before they eventually leak out. But as particles gain more and more energy, they become harder for those magnetic fields to contain. The knee, then, could be the energy at which particles finally break free, streaming out of the galaxy so efficiently that we simply see far fewer of them. This single bend in a graph is more than a data point. It is a boundary line separating the cosmic rays that are born and die within our galactic home from those that may have journeyed from the terrifying voids beyond. If the knee marks the speed limit of our galaxy, then the ankle is the point where we step into an entirely different realm. At an energy of roughly 10 to the 18 electron volts, the cosmic ray spectrum makes its second dramatic bend, curving back upward. This is the ankle, and it represents a profound cosmic border crossing. Here, scientists believe the dominant source of these particles shifts from local galactic accelerators to the vast, violent expanses of intergalactic space. The evidence for this transition is written not just in the energy, but in the very identity of the particles arriving. Below the ankle, the cosmic ray mix is rich with heavier nuclei like iron, forged in the hearts of stars and scattered by supernova within the Milky Way. But above the ankle, the composition appears to lighten, becoming dominated by single protons or the light nuclei of helium. This is a crucial clue. It suggests the particles at these energies are coming from places and processes that either cannot create heavy elements or that strip atoms apart during their unimaginably long journeys. The ankle is the gateway to the ultra-high energy cosmic ray regime, the domain of the Oh My God and Amaterasu particles. Pinpointing its exact location and nature is not just academic. It is the key to understanding where in the universe nature builds its ultimate particle accelerators. Are they colossal jets screaming from the hearts of active galaxies, where supermassive black holes devour matter and spit out energy? Or are they the cataclysmic mergers of neutron stars shaking the fabric of spacetime itself? By studying the ankle, we learn where to point our telescopes. It tells us whether to focus on the familiar stellar graveyards of our own spiral galaxy, or to peer deep into the abyss between galaxies, searching for monsters lurking in the darkness. Crossing the ankle's threshold leads us directly to a prime suspect, a monstrous engine lurking in our own cosmic backyard. Just over 13 million light-years away, practically next door in galactic terms, sits Centaurus A. This peculiar galaxy is a titan of chaos, a testament to a violent past merger that left it with a mangled, dusty shape and a supermassive black hole at its heart that is anything but quiet. From its core, twin jets of matter and energy scream into space for thousands of light-years, visible across the electromagnetic spectrum. This makes Centaurus one of the most powerful and closest active galaxies we know, a perfect candidate for the kind of accelerator that could forge ultra-high energy cosmic rays. For years, scientists have pointed telescopes at this behemoth, searching for the smoking gun. They have found compelling clues, observations of very high energy gamma rays, and more recently, even a few ghostly neutrinos detected by the Ice Cube Observatory at the South Pole seem to point back to Centaurus A. These signals are the telltale signatures of frantic particle acceleration happening within those colossal jets. When protons are accelerated to near light speed, they can collide with surrounding matter or light, creating a cascade of secondary particles, including gamma rays and neutrinos. Finding them is like finding gunpowder residue at a crime scene. The evidence suggests Centaurus is indeed firing a cosmic ray cannon, yet here lies the conundrum. Despite being such a powerful and nearby source, we have not definitively caught it red-handed, sending the very highest energy cosmic rays, the Oh My God class particles, directly to Earth. If it is such a prolific factory, why is its most powerful signature so elusive? The answer may lie in a cosmic maze. The space between galaxies is not truly empty. It is threaded with faint but pervasive magnetic fields, remnants of ancient cosmic events stretching across unimaginable distances. These magnetic fields act like a hall of mirrors for charged particles like protons. A cosmic ray blasted from Centaurus does not travel in a straight line. Instead, its path is scrambled, bent and twisted by these invisible forces over its 13-million-year journey. By the time it reaches us, its trajectory is completely randomized. It points back not to its source, but to a meaningless patch of sky. So the very particles that could convict Centaurus arrive at our detectors with their origin story erased. This magnetic scrambling is why pinpointing the sources of the most energetic cosmic rays remains one of the field's greatest challenges. We see the bullets, we have a suspect with a motive and the right weapon, but the crime scene has been perfectly obscured. The Centaurus, a conundrum, is a stark reminder that in the cosmos, even the most violent events can be shrouded by the faintest whispers of magnetic force. The magnetic maze that hides Centaurus is not the only force erasing the tracks of these cosmic bullets. There is another, even more fundamental barrier written into the fabric of space itself. For the highest energy particles, the universe is not a tranquil void but a thick fog. This fog is the cosmic microwave background, the afterglow of the Big Bang, a bath of ancient photons that permeates every cubic centimeter of the cosmos. In the 1960s, three physicists, Greisen, Zatsepin, and Kuzmin, made a startling prediction. They calculated that any proton traveling with energy above about 10 to the 20 electron volts would not get very far. It would constantly slam into these relic photons. Each collision would be catastrophic, robbing the proton of its immense energy and chipping it down into a shower of less energetic particles. This theoretical limit became known as the GZK cutoff. It meant there should be a hard ceiling on the energy of cosmic rays we can observe from distant sources. No particle from beyond a certain cosmic horizon, roughly 300 million light-years away, should ever reach us with that kind of punch intact. The universe, it seemed, had built its own ultimate speed trap. The mystery deepens with what we actually see. Our largest observatories have indeed detected a steep drop in the number of cosmic rays above that critical energy. The suppression is there, but is it the true GZK effect, or is it simply telling us that the cosmic accelerators themselves, the black holes and star mergers, have a maximum power output and cannot push particles any harder? Distinguishing between these two possibilities is one of the most profound challenges in modern astrophysics. If it is the true GZK cutoff, it confirms a fundamental property of our universe. It means the cosmic microwave background is truly everywhere, just as the Big Bang theory predicts, and it acts as a universal regulator. It also gives us a ruler. By measuring exactly where the suppression occurs, we can learn about the distribution of matter and magnetic fields in the local universe. But if the drop is just due to the limits of the accelerators, then the implications are even stranger. It would mean that the most violent events in the nearby cosmos, for reasons we do not yet grasp, all seem to hit the same energy wall. They roar with unimaginable power but never quite break through that same ceiling. Solving the GZK suppression mystery is not just about cataloging particles. It is about taking the temperature of the universe's oldest light and listening for the maximum volume of its most violent explosions. The answer will tell us if we are seeing a universal law in action or if we are merely witnessing the limits of cosmic monsters. The GZK horizon draws a map of our local universe, a sphere within which the most violent cosmic events can still reach us. One of the brightest landmarks on that map is the Vela supernova remnant. Located a mere 800 light-years away, it is the ghost of a star that exploded in our own galactic neighborhood roughly 11,000 years ago. Its shattered, filamentary glow is a celestial masterpiece, visible even through amateur telescopes. For scientists, Vela is a textbook example, the closest and clearest laboratory we have to study how a dying star becomes a natural particle accelerator. We see the evidence clearly in brilliant gamma rays, the high-energy light produced when accelerated particles slam into surrounding gas. This tells us the remnant's expanding shockwave is indeed doing its job, acting as a powerful cosmic engine. Yet here lies the core of the Vela enigma. While we can see the glow of the accelerator at work, we cannot directly see the specific cosmic ray bullets it fires. The gamma rays are a secondary product, the flash of light from the collision. They tell us particles are being accelerated to tremendous speeds, but they do not tell us exactly what those particles are or their precise energies. Disentangling the pure cosmic ray signal from this cacophony of other radiation is like trying to hear a single instrument in a symphony by only studying the vibration of the concert hall walls. We know the music is playing, but the details of the melody are lost. Vela teaches us a humbling lesson about proximity. Even with a source in our cosmic backyard, the direct detection of cosmic rays at their point of origin remains fantastically difficult. These charged particles are immediately ensnared by the remnants' own tangled magnetic fields, trapped and redirected. Their paths scrambled long before they can escape into interstellar space to begin a possible journey to Earth. So we study the clues left behind: the gamma-ray glow, the structure of the magnetic fields traced by radio waves, the distribution of hot gas seen in X-rays. From this forensic evidence, we build models of the acceleration process. Vela confirms that supernova shockwaves are incredibly efficient particle factories, likely responsible for the vast sea of galactic cosmic rays below the spectrum's knee. But it also underscores the fundamental challenge. To truly understand these engines, we need to catch the particles in the act, a task that requires not just looking at the source, but somehow finding a way to peer inside its chaotic heart. While supernova remnants like Vela fill the galaxy with protons and atomic nuclei, there is another stranger rain falling. Mixed in with the endless downpour of ordinary matter are specks of antimatter, the mirror opposite of everything we see. For every electron, there should be its antimatter twin, the positron. Theory suggested these positrons should be exceedingly rare in cosmic rays, mere side products created when other particles collide in interstellar space. But the data told a different, thrilling story. In 2008, a satellite experiment named Pamela, orbiting high above Earth, made a startling announcement. It detected a clear and growing excess of high-energy positrons. This was not a subtle hint. The number of positrons was rising sharply with energy, far beyond what any conventional model of our galaxy could explain. The discovery was later confirmed and refined with stunning precision by the Alpha Magnetic Spectrometer, or AMS-02, a $2 billion particle physics detector mounted on the International Space Station. This machine has been silently counting cosmic rays for over a decade, and its data paints an undeniable picture. Something nearby is actively producing positrons and injecting them into our galactic neighborhood. So what could possibly be manufacturing antimatter in such abundance? The leading suspect is a celestial object we have already met in a different context: pulsars. These rapidly spinning, magnetized cores of dead stars are natural powerhouses. Their intense magnetic fields can rip particles from their surfaces and accelerate them to fantastic speeds, creating cascades of matter and antimatter in the surrounding nebula. A few nearby pulsars, like Geminga or the Vela pulsar itself, could theoretically be responsible for the positron excess we see. It is a clean, elegant explanation that requires no new physics. Yet the timing and the precise shape of the energy spectrum measured by MS-02 do not match the pulsar model perfectly. The data leaves a tantalizing gap, a space for something more exotic. This is where the dark matter hypothesis ignites the imagination. One of the leading candidates for dark matter is a class of theoretical particles called weakly interacting massive particles. If two of these particles were to collide and annihilate, the theory goes, they could produce a burst of standard model particles, including electrons and positrons. The observed excess could be the faint, billion-year-old echo of dark matter annihilating in the halo of our Milky Way. It would be the first indirect evidence of dark matter's true nature, a discovery that would reshape fundamental physics. The positron excess is therefore a cosmic tug-of-war between two profound possibilities. On one side, a spectacular but known astrophysical engine, the pulsar. On the other, the ghostly signature of the universe's most elusive substance. Solving this puzzle requires more than just counting particles. It requires mapping the entire sky for positrons, looking for a telltale point source that would finger a specific pulsar, or finding a smooth, diffuse glow that would point to dark matter spread throughout the galactic halo. Every new positron counted by MS02 is a vote in this ultimate cosmic election. Antiprotons add another layer of complexity to the antimatter mystery. While positrons are the antimatter twins of electrons, antiprotons are the mirror opposites of the protons found in every atomic nucleus. Their presence in cosmic rays is expected, but for a different reason. Most antiprotons are not created at a source like a pulsar, but are forged in flight. When a high-energy cosmic ray proton, for instance, smashes into a stray atom of interstellar gas, the colossal energy of the collision can transform into new matter. From the wreckage, pairs of protons and antiprotons can spontaneously emerge. This secondary production should account for nearly all the antiprotons we detect, and for decades, the measured numbers seemed to agree beautifully with the models. But as our detectors grew more sensitive, a subtle discordance appeared. The most precise data from instruments like the MS02 spectrometer reveals a slight but persistent excess of antiprotons at certain energies. The numbers are off by just enough to make scientists lean in and look closer. This is the antiproton riddle. The discrepancy is not a thunderclap like the positron excess, but a faint, persistent whisper in the data. It suggests that our understanding of this secondary production process, or the environment in which it occurs, might be incomplete. Perhaps the density of interstellar gas in certain regions is higher than we thought, leading to more collisions. Or maybe the models for how cosmic rays propagate through the galaxy's magnetic maze need a subtle tweak. Yet, just like with the positrons, there is that other, more electrifying possibility. Could this tiny surplus also be a signature of dark matter annihilations? If dark matter particles are colliding and destroying each other, they would not only produce electrons and positrons, but also quarks and gluons that would rapidly coalesce into protons and antiprotons. Finding correlated anomalies in both the positron and antiproton channels would be a much stronger hint than either one alone. It would be like finding two distinct pieces of forensic evidence at the same cosmic crime scene. The challenge is that pulsars and other astrophysical processes can also produce both particles, muddying the waters. Supernova remnants, those giant shockwaves we once thought only accelerated particles, might also be more efficient antimatter factories than our models predict. The shock front itself could create conditions ripe for particle collisions that spawn antimatter directly. So the antiproton riddle forces a difficult question. Are we seeing the first faint cracks in our understanding of ordinary astrophysics, or are we glimpsing the shadow of something entirely new, woven into the fabric of the galaxy itself? Each antiproton counted is a clue, and the jury is still out on what story they are trying to tell. The antimatter whispers lead us to a different kind of cosmic alchemy, one that forges the very elements around us. While we search for exotic particles, ordinary cosmic rays are busy performing a fundamental act of creation. This is the story of lithium, beryllium, and boron. In the grand scheme of the universe, these three light elements are cosmic afterthoughts. The Big Bang produced vast amounts of hydrogen and helium, and stars forge everything heavier from carbon to iron in their nuclear furnaces. But lithium, beryllium, and boron are fragile. They are not cooked in stellar cores in significant amounts, and they are easily destroyed there. So where do they come from? The answer is a violent process called cosmic ray spallation. Imagine a cannonball made of carbon or oxygen, a heavy nucleus accelerated to near light speed by a supernova shockwave. On its million-year journey through the galaxy, it eventually smashes into a slow-moving atom of interstellar gas, usually a humble hydrogen or helium nucleus. The collision is catastrophic. The heavy cosmic ray nucleus shatters like glass, and from the fragments, lighter elements are born. Lithium, beryllium, and boron are the broken pieces of these high-speed wrecks. They are not primary cosmic rays from an accelerator, but secondary products created in flight. This makes them incredibly valuable to scientists. They are not messengers from a source, but diaries of the journey itself. By measuring the abundance of these secondary elements in the cosmic rays that reach us and comparing them to the amount of primary elements like carbon and oxygen, astrophysicists can perform a kind of cosmic archaeology. The ratio tells a story about how long the original particles have been traveling and how much material they have plowed through. It reveals the average path length, the thickness of the galactic material a cosmic ray traverses before it escapes or is destroyed. Think of it like measuring the wear on a stone tumbled in a river. The more smoothed and chipped it is, the longer and more turbulent its journey has been. For decades, this seemed like an elegant solution, but the data has introduced a stubborn puzzle. The observed amounts of lithium, beryllium, and boron suggest a path length that is surprisingly short and strangely shaped. The models based on these light elements indicate that cosmic rays do not travel in a simple, straight line through a uniform fog of gas. Instead, the journey seems patchy. Some particles might travel vast distances through near-empty space, while others encounter dense clouds of molecular gas relatively quickly. This points to a galaxy filled with a clumpy, irregular interstellar medium, a cosmic obstacle course rather than a smooth highway. Even more puzzling are the very highest energy measurements. As we look at cosmic rays with energies approaching the knee of the spectrum, the ratio of these secondary to primary elements seems to change. This could mean that the highest energy particles spend less time confined in the galaxy before they escape, taking a more direct route out. Or it could hint that the spallation process itself becomes less efficient at those tremendous speeds. The lithium, beryllium, and boron problem is a beautiful reminder that the universe leaves fingerprints everywhere. By studying the fragments of broken nuclei, we are not just learning what cosmic rays are made of, but reconstructing the invisible topography of our galaxy, mapping the clouds and voids they have passed through on their epic million-year voyages. From the shattered fragments of our own galaxy, we look out to a city of fire in the void. 12 million light-years away, the starburst galaxy Messier 82 burns with a ferocious intensity. Through a telescope, its core is a breathtaking chaos, a maelstrom of glowing red hydrogen gas and dark, obscuring dust clouds, all torn and stretched by gravitational forces. This is not a place of gentle starlight. Messier 82 is undergoing a frenzy of star formation, birthing new suns at a rate 10 times faster than our entire Milky Way. In this stellar nursery on a galactic scale, massive stars live fast, die young, and explode as supernova in rapid succession, shaking the very foundations of the galaxy. For cosmic ray scientists, this makes Messier 82 something far more valuable than just a pretty picture. It is a natural cosmic calorimeter. In a laboratory, a calorimeter is a device that traps particles to measure their total energy. Messier 82 acts as a galaxy-sized version of this. Its core is so dense with gas and dust, so turbulent from constant explosions, that the cosmic rays produced there cannot easily escape. They are trapped, bouncing around in the chaotic magnetic fields for tens of thousands of years. During this imprisonment, they constantly collide with atoms in the dense interstellar gas. And from these collisions, a telltale signal emerges, a brilliant glow of high-energy gamma rays. Satellites like the Fermi Gamma Ray Space Telescope have seen Messier 82 shining brightly in this light, a direct beacon that confirms it is absolutely teeming with accelerated particles. It is a cosmic ray factory caught in the act, its entire energy output measured by the gamma ray glow it cannot hide. This leads to a profound question about the history of our universe. If a single starburst galaxy is such a prolific producer, what does that mean for the early cosmos? Billions of years ago, the universe was far more crowded, and galaxies collided and merged more frequently, triggering epic waves of star formation. The early universe might have been filled with countless versions of Messier 82, each a blazing furnace of cosmic rays. This suggests that the cosmic ray background bathing the cosmos today could be the accumulated echo of trillions of ancient starbursts, a fossil record of a more violent star-forming youth. Yet the mystery remains: is Messier 82 typical, or is it an extreme outlier? Are all starburst galaxies the dominant cosmic ray factories in the universe, or do other, quieter processes contribute more over time? By studying this brilliant trapped fire, we are not just observing a single galaxy. We are peering back in time, witnessing the kind of engine that may have flooded the infant universe with the first atomic bullets. While starburst galaxies trap their fury, other messengers slip through the cosmic walls unseen. Deep in the Antarctic ice, a cubic kilometer of frozen wilderness has been transformed into a telescope of pure darkness. The Ice Cube Neutrino Observatory does not look for light. Instead, it watches for the faint blue flashes created when an almost nothing passes through our planet. That almost nothing is a neutrino, a ghostly particle so tiny and indifferent it can fly clean through a light year of lead without a single interaction. In 2013, IceCube announced a discovery that changed astronomy forever. It had captured the first definitive evidence of high-energy astrophysical neutrinos coming from beyond our solar system. These were not the gentle neutrinos from our sun, but monsters born in the universe's most extreme environments. Their detection was the smoking gun for a specific kind of violence. Neutrinos like these are only created in hadronic processes, when protons or other atomic nuclei are accelerated to tremendous speeds and then smashed into a target of dense matter or radiation. That collision shatters the proton, creating a cascade of particles, including pions, which then decay into gamma rays and, crucially, neutrinos. So when IceCube catches one of these cosmic ghosts, it is direct proof that somewhere out there, a natural particle accelerator is working with protons. It is the definitive signature of a cosmic ray factory. This forged an unbreakable link between two invisible rains: the charged cosmic rays we struggle to trace and the neutral neutrinos that point straight back to their source. Yet this breakthrough unveiled a deeper layer of the mystery. While a neutrino's path is not scrambled by magnetic fields, making its direction a true pointer, matching a single high-energy neutrino event to a specific cosmic object is like finding a needle in a universe-sized haystack. Even more challenging is connecting a specific neutrino to a specific ultra-high-energy cosmic ray detected years later. The accelerators are not constant. They might blast out a burst of particles and neutrinos in a violent flare, then fall silent for centuries. We are trying to match a single bullet found in one city with a single shell casing found in another, with no guarantee they were fired at the same time or even from the same gun. This challenge is the heart of the multimessenger astronomy revolution. It is no longer enough to just look at the sky with telescopes. Now we must listen with neutrino detectors, feel the ripples of gravitational wave observatories, and catch charged particles with cosmic ray arrays all in concert. The goal is to catch a single cosmic catastrophe in every possible way at once. Imagine a blazar, a supermassive black hole pointing its jet directly at Earth, entering a period of violent activity. If we see it flare in gamma rays, detect a high-energy neutrino from its direction with IceCube, and then, against all odds, measure an ultra-high-energy cosmic ray that backtracks to the same patch of sky, that would be the ultimate conviction. We would have the photon, the neutrino, and the proton itself all telling the same story. So far, we have had tantalizing hints like the neutrino that pointed back to the blazar TXS 0506 plus 056 in 2017, coinciding with a gamma-ray flare. But the definitive multimessenger match that includes an ultra-high-energy cosmic ray remains the holy grail. Every ghostly flash in the ice is not just a discovery. It is an invitation to point every eye and ear in the cosmos toward a single point in the darkness, waiting for the universe to reveal its secrets in unison. While we search for distant accelerators, our own galactic core holds a secret of staggering scale. Emerging from the heart of the Milky Way, two colossal orbs of energy stretch for 25,000 light-years above and below the galactic plane. These are the Fermi bubbles discovered in 2010 by the Fermi Gamma Ray Space Telescope, and they are a monument to some ancient titanic eruption. In gamma-ray light, they appear as two faint, symmetrical lobes, like a giant cosmic hourglass with our galaxy's bustling center at its waist. These are not bubbles of hot gas in the ordinary sense, but vast structures glowing with the signature of high-energy particles. They are essentially a giant reservoir, a cosmic lake filled with trapped cosmic rays and magnetic fields. The particles inside, likely protons and electrons accelerated to fantastic speeds, slam into the thinner gas at the bubble's edges or interact with the light-filling space, producing the gamma-ray glow we see. This makes the bubbles themselves a kind of secondary source, a holding tank for particles that were accelerated somewhere else long ago. The central mystery is the identity of the original architect. What colossal event blew these bubbles into existence? Two prime suspects stand accused. The first is our galaxy's own supermassive black hole, Sagittarius, a star. While quiet today, it may have had a violent past, a period of frenzied feeding where it swallowed vast amounts of gas and dust, could have triggered powerful jets of matter and energy shooting perpendicular to the galactic disk. These jets would have inflated the bubbles over millions of years, pumping them full of energetic particles. The second suspect is not a single monster, but a chorus of stars. The galactic center is a crowded, chaotic place, and it may have experienced a period of intense starburst activity, with hundreds of massive stars forming and exploding in a relatively short cosmic time. The combined shockwaves from all these supernovae could have created a galactic wind so powerful it blew these giant cavities, again filling them with accelerated particles. The debate hinges on subtle clues in the data. The bubbles have remarkably sharp edges, which some models suggest favor a sudden, jet-like event from the black hole. Other studies of the gamma-ray spectrum hint at a population of particles that might be better explained by a longer, more sustained period of star formation. It is a forensic investigation on a galactic scale, piecing together an event that likely ended millions of years before humans walked the Earth. For us, the Fermi bubbles are more than a spectacular mystery. They represent a local, ongoing experiment. They are a vast natural laboratory where we can study how high-energy particles behave, how they are confined, and how they slowly leak out into the wider galaxy. This slow leak means the bubbles are contributing to the very sea of cosmic rays that constantly bathes our solar system. We are, in a very real sense, living in the faint aftermath of a galactic-scale explosion, its remnants still towering over us, whispering secrets about the violent heart of our own Milky Way. The colossal Fermi bubbles remind us that our galaxy has a violent history, but sometimes the most telling clues come from our closest neighbors. Just 800 light-years away, a dead star spins silently in the void. This is the Geminga pulsar, the ghost of a supernova that exploded over 300,000 years ago. To our gamma-ray telescopes, it is one of the brightest objects in the sky, a lighthouse shining not with visible light, but with the high-energy glow of frantic particle acceleration. Geminga sits at the heart of a beautiful, intricate nebula created by its own powerful wind, and for years it has been a prime suspect in the case of the positron excess. The logic is compelling. As this pulsar spins, its intense magnetic field acts like a giant slingshot, ripping electrons and positrons from its surface and accelerating them to nearly the speed of light. These particles stream out, creating the nebula we see and, theoretically, flooding our local region of space with antimatter. Calculations suggest Geminga alone could be responsible for a substantial fraction of the extra positrons detected by experiments like the alpha magnetic spectrometer. Yet when scientists run the detailed models, a frustrating mismatch emerges. The predicted energy spectrum of positrons from Geminga, the specific graph of how many arrive at each energy level, does not align perfectly with the exquisite data collected in orbit. The shape is wrong. The models which account for the pulsar's power, its distance, and the tangled magnetic fields between us produce a curve that is either too steep or too shallow compared to what we actually measure. This is the Geminga anomaly. It forces a difficult question. Are our models of how particles escape from a pulsar's nebula and travel through interstellar space incomplete? Perhaps the magnetic maze between stars is more complex, or the process of acceleration within Geminga's wind is subtly different than we assume. Or, more intriguingly, is Geminga not working alone? This single, bright pulsar might be the one we see clearly, but it could be just the loudest member of a hidden population. The galaxy is likely filled with older, quieter pulsars whose gamma-ray glow is too faint for our telescopes to easily spot. These silent contributors could each add their own trickle of positrons to the galactic pool, and their combined output might perfectly sculpt the energy spectrum we observe. If that's true, then the positron excess is not a signal of dark matter, but a census problem. We have been trying to explain the data with a few famous names, when in reality, a chorus of faint, forgotten voices is doing the work. Solving the Geminga anomaly means looking past the brightest beacons to listen for the whispers in the dark, to determine if we are witnessing a singular cosmic engine or the collective sigh of a galaxy filled with the dead. The journey of a cosmic ray is only half the story, for its violent birth often lights a second beacon in the darkness. When those accelerated protons smash into nearby gas or starlight, they generate a flash of gamma rays, the highest energy light in the universe. This light becomes our distant spyglass, a way to witness cosmic ray factories from across the cosmos. But this spyglass looks through a fog. That fog is the extragalactic background light, the collective glow of every star and galaxy that has ever shone, stretched and diluted across the entire history of the universe. It is the faint cosmic sum of all starlight, a permanent twilight filling the space between galaxies. For a high-energy gamma ray, this serene background is a deadly obstacle course. As the gamma ray travels for millions or billions of years, there is a chance it will collide with one of these ancient, lower-energy background photons. When they meet, they annihilate each other, transforming their energy into a pair of particles, an electron and a positron. The gamma ray never reaches us. It is absorbed by the fog. This process, called extragalactic background light attenuation, means the universe becomes opaque to the highest energy gamma rays over vast distances. The farther away a source is, the more of its highest energy gamma rays get stripped away on the journey. This creates a unique cosmic measuring stick. By observing how the gamma ray spectrum from a distant blazar or starburst galaxy has been trimmed at the high energy end, scientists can, in principle, gauge the thickness of the fog it traveled through. That thickness relates directly to distance. It offers a way to measure cosmic distances independently of traditional methods, and more importantly, to peer behind the curtain and calculate the true, intrinsic power of these monstrous accelerators. We can try to determine how many cosmic rays they are actually producing, not just the dimmed glow that survives the trip. The enigma lies in the fog itself. We cannot point a telescope at the extragalactic background light directly. It is too diffuse. Our models of it are built from countless assumptions about galaxy formation, star formation rates across cosmic time, and the dust that obscures starlight. These models have large, haunting uncertainties. If we misjudge the density of the fog, we completely miscalculate both the distance to the source and its true power. It is like trying to judge the wattage of a lighthouse during a misty night without knowing exactly how thick the mist is. This fundamental uncertainty reverberates back to our hunt for cosmic ray origins. A gamma-ray source we think is moderately powerful and relatively nearby based on an attenuation model. could in reality be a mind-bogglingly powerful engine much farther away, its signals savaged by the fog. Or the reverse could be true. This means the map we are trying to build of the universe's particle accelerators, the very map we need to trace back the highest energy cosmic rays, is drawn on shifting, nebulous ground. The extragalactic background light is both a crucial tool and a profound obstacle, a reminder that to see the most violent events, we must first learn to see the universe's gentlest, most pervasive glow. This fog of ancient starlight obscures our view, but the fundamental mystery remains even closer to home. We have caught the bullets, these cosmic rays with the energy of a tennis ball served at professional speed, yet we cannot find the gun. This is the central detective story of ultra-high energy cosmic rays. We know they exist, we measure their staggering power, but the sky refuses to point a clear finger at their origin. The list of suspects is a catalogue of cosmic monsters. Could the culprits be active galactic nuclei, where supermassive black holes devour matter and spew jets of plasma across millions of light years? Their sheer power makes them prime candidates, or perhaps the sources are fleeting and catastrophic, like gamma-ray bursts, the single most luminous explosions in the universe, thought to be the birth cries of black holes or the collisions of neutron stars. They have the raw energy, but their bursts last only seconds, making it a cosmic coincidence to catch both the gamma-ray flash and a cosmic ray from the same event. Another violent suspect is a tidal disruption event, when a star wanders too close to a black hole and is shredded into a luminous stream of debris. These are monstrous, one-time eruptions that could certainly accelerate particles to incredible speeds. And beyond these, theorists imagine even more exotic phenomena like defects in the fabric of space-time left over from the Big Bang, or the decay of hypothetical super-heavy particles from the early universe. We have a lineup of suspects, each capable of immense violence, but none have been conclusively caught in the act. The reason turns the entire sky into a scrambled map. Remember, these cosmic rays are not neutral photons or ghostly neutrinos. They are charged particles, almost always protons or atomic nuclei, and our universe is threaded with magnetic fields, faint but pervasive, stretching within and between galaxies. As a proton travels for millions of years from its source to Earth, these magnetic fields act like a hall of mirrors in a funhouse. They gently but constantly bend the particle's path. By the time it finally strikes our atmosphere, its trajectory is completely randomized. It points back not to its true source, but to a meaningless point in the void. Imagine trying to find the source of a river by studying a single, rain-soaked leaf floating in the ocean. The leaf's journey has been so twisted by currents and winds that its origin is utterly lost. This magnetic deflection is why a cosmic ray detected over Utah might appear to come from an empty patch of sky near the constellation Ursa Major, while its true birthplace could be a brilliant active galaxy in the direction of Centaurus. We are not just looking for a needle in a haystack. We are looking at a haystack where every piece of straw has been deliberately bent to point in the wrong direction. This scrambling forces scientists to think in terms of statistics, not single events. They must collect thousands upon thousands of these ultra-high energy detections and look for subtle statistical overdensities, faint smudges on the sky map where slightly more particles seem to arrive. It is a painstaking process of building a picture one scrambled pixel at a time, hoping that eventually a shape will emerge from the chaos, pointing us toward the universe's most powerful hidden accelerators. This magnetic scrambling is a cosmic puzzle in itself, a labyrinth we must learn to navigate from the inside out. Our galaxy's magnetic field is not a simple bar magnet with neat north and south poles. Instead, it is a chaotic, tangled web, woven from the threads of countless supernova explosions and stellar winds over billions of years. Picture it as a stormy sea, with waves and currents of magnetic force flowing in all directions, their strength shifting from one region of space to the next. When a charged particle like a proton enters this sea, it does not sail a straight course. It gets caught in the currents, its path spiraling and bending around invisible lines of magnetic force. The higher the particle's energy, the straighter its path can be, fighting against the magnetic push. But for most cosmic rays, especially those below the ultra-high energy regime, the deflection is severe. A particle born in a supernova on the far side of the Milky Way might perform a dizzying, corkscrewing dance for millions of years before it finally, randomly, exits the galaxy or plunges into our atmosphere, its origin story completely erased. So how can we possibly map a maze we cannot see, using messengers that have forgotten where they came from? The answer lies in reading the subtle patterns in the chaos. By analyzing the arrival directions of millions upon millions of lower-energy cosmic rays, scientists can perform a kind of statistical tomography. If the magnetic field were perfectly uniform, the cosmic ray sky would look perfectly smooth. But because the field is tangled and clumpy, it creates faint, blurry hotspots and cold spots in the cosmic ray map. These are not the sources, but the shadows of the magnetic landscape itself. It is like studying the patterns of leaves swirling in a turbulent river to deduce the hidden rocks and currents below the surface. Every twisted path recorded by our detectors is a single data point helping to chart the invisible architecture of our galactic home. The ultimate goal is to build a precise, three-dimensional model of the Milky Way's magnetic field. This is a monumental task requiring input not just from cosmic rays, but from observing the polarization of starlight, the glow of radio waves from synchrotron radiation, and more. Better magnetic field maps are not just an academic exercise, they are a decoder ring. If we can accurately model how the field scrambles trajectories, we can then run the tape in reverse for the highest energy events. We could take the arrival direction of an oh my god particle and, using our magnetic model, rewind its path through the galactic maze to see where it might have entered the Milky Way from intergalactic space. This would narrow the search for its source from the entire sky to a much smaller window. There is another, more promising clue. Not all cosmic rays are simple protons. Some are heavier nuclei like carbon, oxygen, or even iron. These carry more electric charge, which means the galactic magnetic field grips them even more tightly, bending their paths more severely. That might sound like a disadvantage, but for the very highest energy events, it could be a key. If we ever detect an ultra-high energy cosmic ray that is definitively a heavy nucleus, its extreme energy would help it fight the magnetic pull, but its high charge would still leave a unique signature in its deflection. The hope is that by identifying the chemical fingerprint of such a particle and modeling its specific journey, we could get a much more precise backtrack than with a proton. It would be like following a brightly painted boat through the stormy sea instead of a plain wooden raft. The galactic magnetic maze has long been the enemy of cosmic ray astronomy, obscuring our view of the universe's most powerful events. But now we are learning to read the maze itself, transforming it from an obstacle into a guide. Each scrambled path is a thread in the map, and we are slowly, painstakingly beginning to trace it back to the source. The galactic magnetic maze is not the only force shaping the particles we detect. Their very identity tells a deeper story. At the very highest energies, the cosmic ray composition itself holds a startling surprise. For years, many scientists expected that the most powerful cosmic rays, the ones like the oh my god particle, would be simple protons. The logic was compelling. Protons are the lightest and most common nuclei, and they are the easiest for an accelerator to fling to unbelievable speeds. But data from the world's largest cosmic ray observatory, the Pierre Auger Observatory in Argentina, has painted a more complex and puzzling picture. As they analyzed thousands of ultra-high energy events, they noticed a subtle but significant trend. The composition seemed to be shifting. Rather than a pure beam of protons, the evidence suggested a growing fraction of these monumental bullets were heavier nuclei all the way up to iron. An iron nucleus is a cosmic cannonball compared to a proton's bullet. It contains 26 protons and typically 30 neutrons, making it 56 times heavier. For something that massive to reach such a staggering energy means the accelerator behind it must be almost incomprehensibly powerful. This is the iron nuclei surprise, and it forces us to rewrite the narrative of the universe's ultimate particle accelerators. If the highest energy cosmic rays are indeed heavy nuclei like iron, it dramatically narrows the list of possible sources. It points to environments rich in these heavy elements, places where stars have lived, died, and forged iron in their cores before scattering it back into space. This makes stellar graveyards like the dense regions around supermassive black holes or the remnants of many supernova more likely suspects than, say, the relatively pure hydrogen found in the vast voids of intergalactic space. An active galactic nucleus with its swirling disk of stellar debris and powerful magnetic fields becomes an even more compelling candidate. Such an environment could scoop up these heavy nuclei and hurl them outward in its jets. But the mystery deepens with the journey. Could this shift in composition be an illusion created by the trip itself? A proton on its million or billion-year voyage is fragile. It can be stripped apart if it collides with the pervasive photons of the cosmic microwave background, that fossil radiation from the Big Bang. This process, called photodisintegration, could destroy a high-energy proton long before it reaches us. An iron nucleus, while heavier, is actually more robust against this particular kind of erosion. It might lose a few neutrons along the way, but its core can survive. So the iron we see might not be what was originally launched. We could be witnessing the durable survivors of a long and brutal journey, while the protons that started alongside them have simply faded away. This means the sources might still be accelerating a mix of particles, but only the heaviest make it across the cosmic finish line to our detectors. This single clue, the potential weight of these particles, changes everything about how we search for their origins. If they are heavy nuclei, they carry more electric charge. That makes them far more susceptible to deflection by galactic and extragalactic magnetic fields. Their paths would be scrambled even more severely than a proton's. This could explain why we see such a diffuse, seemingly random pattern of arrival directions for ultra-high energy events. We are not looking at a map of sources, but a map of a magnetic storm with the heaviest particles tossed around the most. It also raises a profound question about the accelerators themselves. Pushing a single iron nucleus to the energy of a thrown baseball requires an engine of monstrous sustained power. It cannot be a fleeting, one-second blast like a gamma-ray burst. It must be a steady, cosmic dynamo that can contain and accelerate these heavy particles over a significant distance, like the immense shock front of a galaxy cluster merger or the relentless jets of an active black hole. The iron nuclei surprise forces us to look not for the brightest flash in the sky, but for the most powerful and patient cosmic machine, one that can forge atomic cannonballs and fire them across the universe. The story of the highest energy cosmic rays is no longer just about speed. It is about mass, endurance, and the hidden forges that build the universe's most formidable projectiles. The possibility of iron nuclei surviving the journey introduces a critical test for one of cosmology's great speed limits. The Greisen-Zatsepin-Kuzmin cutoff was supposed to be an absolute barrier, a point where the universe itself says no more. Yet, the history of cosmic ray science is written in the exceptions to every rule. A handful of events, perhaps fewer than a dozen across decades, have been recorded with energies so high they seem to brush against or even exceed this theoretical ceiling. These are the super GZK events, and they are the most scrutinized data points in the field. Each one arrives as a profound contradiction. If the GZK process is real and our models of the cosmic microwave background are correct, these particles should not exist. They should have been stripped of their energy by collisions with that primordial light long before reaching Earth. Their very detection then forces a brutal interrogation. Is our measurement wrong? Is our theory incomplete? Or is the universe showing us something entirely new? The first possibility is always the most careful. Could a subtle calibration error in a giant detector array, a freak atmospheric effect, or a rare statistical fluctuation mimic an energy that was never truly there? Scientists spend years reanalyzing the data from these singular events, checking and rechecking every circuit, every sensor, every line of code. The integrity of the entire field depends on this ruthless skepticism. But if the events hold up under this scrutiny, the implications become staggering. One explanation points back to the composition. Perhaps these are not protons at all, but heavier nuclei like iron. A heavy nucleus at the same total energy actually has less energy per constituent proton and neutron, which might allow it to slip under the GZK radar for a longer distance. It is not truly super GZK, but a clever cosmic loophole. Another, more radical idea is that these particles are not coming from far away at all. If an accelerator exists within our local group of galaxies, just a few million light-years away, a particle might not have traveled far enough through the fog of background light to be fully eroded. It would be a nearby monster hidden in plain sight. Then there is the most thrilling possibility of all: new physics. Could these events be the decay products of exotic, super-heavy dark matter particles, relics from the universe's first moments that are only now disintegrating in the halo of our galaxy? Such a decay would happen essentially at our doorstep, bypassing the long intergalactic journey and its GZK attrition entirely. Or do they hint at flaws in our understanding of particle interactions at energies far beyond anything our particle colliders can reproduce? Each super GZK event is a crack in the foundation of modern physics. They are not just cosmic rays, they are potential portals. Finding a few more of them, mapping their arrival directions, and crucially, identifying what they are made of, could force a rewrite of the textbooks on particle physics, cosmology, and the fundamental limits of the universe. The hunt is not for more of the same, but for the one extraordinary event that finally breaks the ceiling for good. These particles that might rewrite physics also touch the very air we breathe. Beyond the search for cosmic monsters lies a quieter, more intimate mystery. Could the rain of atomic bullets from space be changing our planet's weather? This is the cosmic ray climate connection hypothesis, a bold and controversial idea that links the most energetic events in the universe to the formation of clouds over our heads. The proposed mechanism is elegant in its simplicity. As a cosmic ray, usually a high-energy proton, streaks into the upper atmosphere, it smashes into air molecules, shattering them and creating a cascade of secondary particles. This cascade ionizes the air, stripping electrons from atoms and creating charged molecules. These ions, the theory suggests, can act as seeds for tiny aerosol particles. In the right conditions, water vapor in the atmosphere prefers to condense around these small seeds. More seeds could lead to more cloud droplets and potentially to more clouds. Since clouds reflect sunlight back into space, an increase in low-level cloud cover could cool the planet. The enigma hinges on a cosmic variable, the sun. Our star's magnetic field acts as a shield for the solar system, deflecting many galactic cosmic rays away from Earth. When the sun is active with a strong magnetic field during solar maximum, fewer cosmic rays reach us. When the sun is quiet during solar minimum, the shield weakens and the cosmic ray flux increases. Some researchers have noted correlations over centuries between periods of low solar activity, high cosmic ray flux, and cooler global temperatures like the historical Little Ice Age. This suggests a possible natural thermostat where the sun's changing mood, mediated by cosmic rays, influences cloud cover and climate. Laboratory experiments like those at the CERN cloud chamber show that ionization from cosmic ray mimics can indeed enhance the formation of certain types of aerosol clusters. It is a real, measurable effect, Yet the leap from a lab result to a global climate driver is where the scientific debate turns fierce. The central controversy is whether this ionization effect is strong enough to create a significant number of cloud condensation nuclei, the specific particles that actually grow into cloud droplets, and whether any change in cloudiness would be large enough to meaningfully impact global temperatures. Many climate scientists point out that the observed correlations over recent decades are weak or inconsistent, and that other factors like human-made aerosol pollution and greenhouse gases overwhelmingly dominate climate trends. The cloud system itself is incredibly complex, with countless variables influencing formation and lifespan. Isolating the signal of cosmic rays within that noisy, chaotic system has proven extraordinarily difficult. So the hypothesis remains an enigma, suspended between intriguing possibility and unproven influence. It is a reminder that our planet does not exist in isolation. We are bathed in a sea of invisible particles from distant cataclysms, and the question of whether they leave a fingerprint on our daily weather is one of the most profound connections between the cosmic and the familiar. It turns the sky above us into a vast natural laboratory where the universe itself might be conducting a subtle, billion-year-long experiment. That subtle whisper in the positron and antiproton data leads us to the ultimate cosmic detective story. Beyond the known monsters like pulsars and black holes, scientists are hunting for a signature written in the rain itself, a faint pattern that could finally reveal dark matter. This invisible substance makes up over 80% of the matter in the universe, yet it has never been directly seen. It does not emit, absorb, or reflect light. But there is a tantalizing possibility. Dark matter might announce its presence by destroying itself. According to leading theories, dark matter could be made of particles that are their own antimatter opposites. If two of these particles collide, they would annihilate in a flash of pure energy, transforming into a spray of familiar particles we can detect, including electrons, positrons, protons, antiprotons, and gamma rays. These secondary products would then join the great cosmic ray sea, creating subtle bumps or excesses in the energy spectra that our space-based detectors measure. This is the dark matter signature hunt, and cosmic rays offer our most promising window into this invisible realm. Experiments like the alpha magnetic spectrometer on the space station are not just cataloging particles. They are forensic scientists sifting through a cosmic haystack, looking for the unique needle of a dark matter decay. The challenge is monumental because every potential dark matter signal has a plausible astrophysical twin. An excess of positrons could come from a nearby pulsar. A bump in antiprotons might be explained by better models of cosmic ray collisions with interstellar gas. A peculiar line in the gamma ray spectrum could be instrumental noise or an unknown atomic process. To claim a discovery, scientists must rule out every conceivable ordinary explanation, a task that requires mapping the entire sky with incredible precision. They look for clues in the shape of the signal. A dark matter signal from the smooth halo of our galaxy would look diffuse, coming from all directions. A signal from a pulsar, however, would likely point back to a specific location. They also search for unique fingerprints, like a sharp spike at a very specific energy in the gamma ray data, which would be very hard for any known astrophysical process to mimic. The hunt is a race against cosmic confusion, a struggle to hear a single, faint note in a symphony played by the universe's most violent instruments. Finding that note would not just solve the mystery of cosmic rays, it would illuminate the hidden architecture of reality itself, revealing the true nature of the dark universe that holds our galaxy together. That hunt for a faint signal in the noise finally found its first promising landmark. After decades of staring at a sky scrambled by magnetic fields, the Pierre Auger Observatory in Argentina saw a pattern emerge. In the data from tens of thousands of the highest energy cosmic rays, a broad, diffuse hotspot glowed on the map, centered on a patch of sky near the constellation Centaurus. This was not a single, brilliant point of light. It was a statistical smudge, a region about 40 degrees across where these ultra-high energy particles arrived about 6% more often than pure chance would allow. In the world of cosmic ray astronomy, where sources are hidden by a funhouse mirror of magnetic deflection, this was a monumental discovery. It was the strongest clustering hint ever found, the first real evidence that these incredible bullets might not be coming from everywhere at once, but are funneled toward us from specific corners of the cosmos. The location of this hotspot is what makes it so tantalizing. It points roughly toward the same general part of the sky that houses our galactic neighbor, Centaurus A, that monstrous active galaxy with its colossal jets. But the hotspot is far too big and blurry to be Centaurus alone. Instead, it suggests a whole neighborhood of violence. This region of space is rich with structure, containing not just Centaurus A, but other nearby active galaxies and a dense knot of matter known as the Virgo cluster. The leading theory is that we are not seeing a single cosmic gun, but the combined glow from an entire cosmic battlefield. Multiple accelerators within that general direction, active galactic nuclei, galaxy cluster mergers, or other unseen engines, could all be contributing to the haze of particles. Their individual beams are twisted and smeared by intergalactic magnetic fields over millions of light years, blending together into that single, broad excess on our sky map. It is like standing downwind from a city at night and seeing a general glow on the horizon without being able to pick out any single street lamp or building. The Auger hotspot is that glow proof that something powerful is happening in that sector of the universe. The future of this search hinges on building a bigger net. The current observatory, vast as it is, has collected enough of these extremely rare events to see the smudge, but not to resolve its details. Next-generation observatories, like the planned Auger Prime upgrade or the ambitious giant radio array for neutrino detection, aim to catch these particles in far greater numbers. With more data, scientists hope to see if the broad hotspot sharpens into smaller, tighter clusters within it. Could we eventually resolve individual sources within that glowing haze? The answer will tell us if we are looking at a single dominant monster surrounded by fainter contributors, or a true chorus of cosmic accelerators all singing in the same key. This diffuse glow near Centaurus is more than a data point. It is a signpost. After a century of searching through a scrambled sky, it finally gives us a direction to stare. While the Auger hotspot points to a bustling galactic neighborhood, its northern counterpart tells a story of profound emptiness. The telescope array, a sprawling network of detectors across the Utah Desert, has mapped its own mysterious excess of ultra-high-energy cosmic rays. This northern hotspot covers a patch of sky in the constellation Ursa Major, the Great Bear, and it is just as statistically significant as the southern one. Yet when astronomers point their most powerful telescopes toward this region, they see almost nothing. No brilliant active galaxies, no dense clusters of merging star systems. Just the quiet, diffuse glow of the local void, that same desolate expanse of space that birthed the Amaterasu particle. This creates a stunning cosmic contradiction. We have a clear statistical signal that something in that direction is firing unimaginably powerful atomic bullets at Earth, but when we look, we find only a cosmic desert. The contrast with the Auger hotspot could not be sharper. One points to a region rich with potential accelerators, a cosmic cityscape. The other points to a vast, empty field. This forces a radical rethinking of our assumptions. Perhaps the sources are not the brilliant beacons we expect. Could they be hidden behind thick veils of dust, completely obscured from our optical and gamma-ray telescopes? Or, more intriguingly, are we seeing the effects of something far larger and more structured than individual galaxies? This is where the plot deepens into the architecture of the cosmos itself. Both the Auger and telescope array hotspots appear to lie along a ghostly highway known as the supergalactic plane. This is not a physical structure you could see, but a vast, flattened plane of enhanced density, a web of galaxy clusters, filaments, and superclusters that defines the largest scale structure in our local universe. Our own Milky Way sits within this plane like a speck of dust on a gigantic, invisible sheet. If these cosmic ray hotspots are truly aligned with the supergalactic plane, it suggests a breathtaking possibility. The accelerators may not be isolated monsters, but are instead embedded within this colossal framework. The particles could be accelerated by shocks from the merger of entire galaxy clusters along these filaments, or by turbulent magnetic fields that span millions of light years within the plane itself. The supergalactic plane could act as a cosmic waveguide, a channel that funnels and directs these high-energy particles, explaining why we see hotspots in specific, aligned directions rather than a perfectly random sky. This alignment would mean that the origin of the most energetic particles in the universe is not a local mystery, but a structural one. They are not just coming from a galaxy, but from the skeleton of the cosmos. The empty northern hotspot, then, might not be empty at all. It could be a window into a section of this vast plane where the acceleration is happening in the dark, diffuse spaces between the glittering cities of stars, powered by the slow, gravitational dance of the universe's largest building blocks. We are no longer just hunting for cosmic guns. We are learning to read the blueprint of reality and finding that its hidden seams might be crackling with unimaginable power. The supergalactic plane's hidden architecture may be the key, but to map it we need a new generation of eyes. This brings us to the final, and perhaps most hopeful, cosmic ray enigma, the future of the hunt itself. The next decade will see the launch of observatories so ambitious they will transform our blurry, scrambled map of the universe into a high-definition portrait. Leading this charge is the Cherenkov Telescope Array, or CTA. Instead of catching particles directly, CTA will watch for the fleeting blue flashes of Cherenkov light created when gamma rays from cosmic accelerators strike our upper atmosphere. With over 100 telescopes spread across sites in Chile and the Canary Islands, it will be the most sensitive gamma-ray observatory ever built, seeing fainter sources and measuring their energy spectra with razor-sharp precision. It will essentially take a cosmic census of particle accelerators, identifying thousands of active galactic nuclei, pulsar wind nebulae, and supernova remnants, and telling us exactly how hard each one can punch. But gamma rays are only one messenger. To triangulate the truth, we need to listen for others. That is the goal of the Giant Radio Array for Neutrino Detection, or GRAND. Envisioned as a colossal network of 200,000 radio antennas spread across mountains in China, GRAND will hunt for the most elusive signal of all, ultra-high energy neutrinos. When a neutrino of unimaginable power interacts in the atmosphere or even in the lunar soil, it can trigger a cascade of particles that emits a faint radio pulse. GRAND aims to catch these whispers, providing pristine pointers back to their sources, completely unaffected by magnetic fields. It is a direct line to the hadronic accelerators we seek. Perhaps the most revolutionary concept waits above the atmosphere altogether. The probe of extreme multi-messenger astrophysics, or POEMMA, is a proposed satellite mission with a breathtaking design. 2 spacecraft would fly in formation, staring down at Earth's dark limb. Their job is to capture the faint ultraviolet fluorescence and optical Cherenkov glow of ultra-high energy cosmic ray and neutrino showers from the ultimate vantage point, space. Free from the atmospheric interference that limits ground arrays, POEMMA could survey the entire sky with uniform sensitivity, catching the rarest events in numbers we can only dream of today and measuring their nuclear composition with unprecedented accuracy. Together, these projects represent a fundamental shift. we are no longer building mere detectors, we are constructing a unified sensory system for the cosmos. CTL will show us the gamma-ray glow of the accelerators, GRND will listen for the neutrino whispers from within them, and POEMM will catch the actual cosmic ray bullets in vast numbers, with their paths and identities clearer than ever before. By combining these messengers in real time, we will move from seeing smudges on a map to watching the cosmic machinery operate. We will witness a single blazar flare and see its neutrino, its gamma-ray burst, and perhaps even a clutch of ultra-high-energy cosmic rays all arrive in concert, telling one coherent story. The great enigmas, the origin of the oh my god particle, the nature of the Auger hotspot, the fingerprint of dark matter will not be solved by a single lucky detection, but by a flood of data from these new eyes and ears. The rain of atomic bullets has been a mystery for a century. For the first time, we are building an umbrella sophisticated enough to catch every drop, analyze its trajectory, and trace it all the way back to the storm. The universe's most powerful accelerators have hidden in plain sight for eons. Their time in the shadows is almost over. From solitary bullets with the energy of a baseball to vast, whispering patterns on the sky, these 25 enigmas form a single, sprawling mystery. They are not just random space weather. They are the shattered pieces of a cosmic puzzle, each one a direct probe into the most violent events the universe can muster. We have followed their trail from the ghostly whispers of antimatter to the colossal shockwaves of galaxy clusters, from the scrambled maps of our own magnetic galaxy to the empty voids that somehow fire atomic cannonballs. Every anomaly, every excess, every impossible particle is a question written in energy. Are we seeing the limits of physics or its next chapter? Are the answers hidden in the brilliant hearts of active galaxies, or in the dark, invisible scaffolding that holds reality together? This silent rain has been falling since the dawn of time, a constant reminder that our quiet corner of space is connected by invisible threads to the most extreme frontiers of existence. To study cosmic rays is to become a cosmic detective, sifting through the aftermath of explosions we cannot see to understand the forces that shape everything. The hunt is accelerating, with new observatories rising from deserts and mountains, and even looking down from orbit, we are on the verge of turning these enigmatic clues into a coherent picture. The universe's ultimate particle accelerators will not stay hidden forever. Which of these puzzles captures your imagination the most? Is it the solitary terror of the oh my god particle, the eerie silence of the northern hotspot, or the tantalizing whisper of dark matter in the positron rain? Let us know in the comments below. For more journeys into the deepest mysteries of space, be sure to subscribe. The cosmos is speaking in a rain of atomic bullets. We are finally learning how to listen.